well, I should say, I know why, but it's not as bad as people make it out to be. So the first thing I want to talk about is I want to talk about the difference between a difference and a variation, all right? And you have to bear with me for a couple minutes while we get this notion pointed out. We're going to have two things we're going to be dealing with. We're going to have points, and then we're going to have functions. Okay? So the way we do this is, points we say, when we have a vector, say x. I'm going to say x is an element of Rn. Okay? What this means is that I have, if you write this out, what it means is x, which is x1 up to xn, is an element of Rn, and I denote it as a column vector. Okay? On the other side, when I'm dealing with functions, it doesn't work this way. All right? Functions, you have to say function x, and it's got an argument, something. I don't know what that argument is. You call it whatever you want to call it. It is a function, is an element of Rn. What I mean by that is, if I put a value into this argument, I say x of t is equal to x1 of t up to xn of t. That is an element of Rn. But over here, I deal with the fact that x directly is an element of Rn, but the function itself, what I'm saying is, if I write this actually right like that, let's just do it this way for a second. What I'm saying is that the function x of dot lies in a set, call it omega, where omega is a function space. Okay? It's not a space of points. It's a space of functions. What I say over here...
Professor Rock?
Yes.
Microphone's not on.
It's not?
No, sir.
Oh, I thought I turned it on. I think I turned it off.
I think you turned it off.
Yeah, I'm sorry.
The student mic, so you're good with
Okay.
that, but I want to do better.
That's fine. Okay. Okay, can you hear me now? I'm sorry. I apologize. Yeah, no problem. So over here, what I'm saying is I'm saying the point x lies in n-dimensional real space Rn, okay? You cannot get these two things confused. These are points, these are functions, all right? Functions are not points. You can evaluate a function at a point to give you back a set of numbers. But the function itself is not a point. Over here, I'm dealing with actual points, all right? So when we do things with these, especially when we're talking about the concept of derivative, or, let's start with derivative. It doesn't apply the same way to functions that it does to points, all right? If I have a function, now let's talk about two things here. I'm still on this thing with points and functions, all right? So this column is continued. You don't have to write it twice, okay? Think about this now in a slightly different way. Let's suppose I have a function, f of x. F of x is a function, okay? And that function is such that f maps vectors from Rn into Rm. That makes sense to everybody, right? I have a point, I apply the function to that point, I get back a value, right? So what does a function produce for me? It produces for me a value. Now, let's think about this from the standpoint of a function. I start with a function instead of a point, all right? If I start with a function, say x of t, what would be required in order to produce back a point or a value? Think about it. I have a whole function, all right? This is hard to do. But think of it, imagine it this way. You have a function of time. Now, I take this function of time, and I want to operate on it in some way. I want that operation to produce back for me a value. So the same thing that I'm doing over here. I want to put in a function, and I want to get back an m-dimensional value, right? How can I do that? Does it make any sense to do that? Let's just take an example, all right? So I'm going to do the same thing over here. I'm going to write it out first, and then we'll talk about it in a little bit. Suppose that well, let's make this a little easier. Let's just go into reals, okay? I can go into m-dimensional space later. Let's suppose I have something which, when I operate on a function, gives me back, I call this thing a functional. I'll explain it in just a minute. Where what f does is it takes things inside the set omega, which is my function space, and it gives me back a real number. Can you think of something that does that? Give me an example of something that does that. So let's take an example. This will be a little bit clearer. All right, for example, let's suppose x of t is equal to sine of t. That's a function, right? What would I need to do to that thing to produce back for me a real number? Right? Now, I'm not asking you to evaluate the function at a point. Don't misconstrue what I'm asking. I'm saying I want something that when I operate on the whole function gives me back a value. Can you think of something that you've done in your life that actually does that? And when I tell you, you say, oh, yeah, that's obvious. And I'll say the same thing. If it's obvious, you should have been able to tell me. So therefore, it's not obvious, all right? Yeah. Integration, right? If I say that I'm going to say the integral from a to b of x of tau d tau, which in this case would be the integral from a to b of sine of tau d tau. And by the way, I use tau here because I don't want you to get confused. This is a dummy variable, all right? It's a dummy variable of integration. What does this produce back for me? Please don't integrate this, all right? Tell me what I get when I'm all done. What do I get? I don't want the answer. What do I get? I just want to know what kind of quantity do I get? No, not area. Okay, area. What does this produce for me? You're not thinking the way that I'm trying to get you to think over here. I'm trying to get you to say the end result is a real number. What does this produce for me? I don't know what A and B are. I haven't told you what they are. They could be anything. What's the end result of doing this? You're trying to calculate it. I said don't calculate it. I can see you're trying to calculate it because you're sitting there doing this. What is it that this produces for you? I say I have a function, x of t. I integrate it from a to b. What does the result of that always have to be? A what? A real number, right? I don't know what it is. I don't care what it is. It gives me back a real number, right? What it does, but what's the input? What's the input to this operation? What's the operation, first of all? Integration, right? So the operation is integration from A to B. What's the result? A real number, right? The input is not a number. The input is a function. It's the integration of a function from A to B. The input is not a number. The input is itself a function, right? So therefore, this cannot be a function. It's a function of a function, right? Yes, the input's a function. There's a function that's operating on the function, giving me back a real number. This is what we call a functional. It's different from a function. It doesn't take in numbers. It takes in functions, right? So this is what this whole thing is about. Is we say a function, this is the distinction that I'm trying to make, is an operation on elements x in Rn that produce a real number. That's a function, right? But a functional, I don't like this job. A functional is an operation on a function. And we denote this x of dot in this set omega, which is my function space, that produces a real number. Why does this matter? Okay, now let's think about this. In a bigger sense, all right? Optimal control is a subject where the goal is to determine a control. What is a control? Tell me something. Can somebody tell me what a control is? Have any of you, I hope all of you have taken some class in control, so you know what a control is. What's a control? Or I should say it this way, you think you know what a control is. What's a control?
It's an input.
It's an input. But what is it? In the context of what I'm talking about. It's a function of what?
Time.
Usually a function of time, right? Because we usually take time to be the independent variable, right? It's a function of time. At each value of time, there's a value of this thing that you generally call u, right? You say u of t, right? What does it mean to control a system? It means that at each instant of time, I'm assigning a command saying, I want you to do this. This is my input to the system. Given this input, I want you to do something, right? That's what you're saying. Control, what does control imply? Control has an implication. A lot of people don't understand what that implication is. What does it mean? The implication of control is that you have the freedom to choose it, right? Nobody's telling you it has to be something. You're saying, I'm going to tell you this is what it is. Now use what I'm telling you to use, right? That's the whole point of control. Otherwise, you don't have control, right? When you say I have control of something, it means that you can make it do what you want it to do because you can change the input to the system to get it to do what you want it to do. That's the whole concept of control. Now, in reality, nobody actually has infinite control, right? We all have finite control. Clearly, we can't do things, just anything we feel like doing. But within some range, we could say I can do anything within this range. That's my set of allowable controls. But the input is a function. In optimal control, the goal is to determine a function and a path, which is a corresponding path that the system is going to then take that will achieve some goal in the best way possible. So what is it that you're trying to solve for? You're trying to solve for functions. You're not solving for points. You're not determining a point. You're determining a whole function that says, I want this whole function given the parameters of the problem that I've described, which is I want the function that steers my system in such a way that it achieves some goal in the best way possible, right? I may want to go from here to the mall, and I want to use the least amount of fuel possible, right? But I have what's my system? My system is going to be my car, right? I'm going to drive my car, right? My car has some dynamics associated with it. So it's going to be a dynamic system, right? So generally speaking, you got a dynamic system that has that you can affect its motion by certain controls. In a car, you can steer it, you can hit the accelerator, you can hit the brake. Those are all controls, right? You can change what the car does by doing that, right? So the point is that you're solving for functions. You're not solving for points. So now, given this setup here, we have to have a way of dealing with the next construct, which is that what does it mean to change a function? You know what it means to change a point, right? If I have a point, let's say I've got x, which is an element of Rn. Suppose we want to increment x by some amount. Let's suppose I call that amount delta x, right? Then the amount of the increment, or the new value of x will be x plus delta x, right? What does this delta mean? This delta means the amount of the increment of x, right? So the thing that I'm using here, delta, is the symbol that represents the increment, or an increment, in x. But now what's true about x? X is a point, right? So I'm going to be more clear here. It's a point in Rn, right? And I'm going to increment it by some amount. Suppose now I do the same thing for a function. I have a function. Suppose now that x of t is a function of t. What does it mean to increment a function? What do you have to do? Let's draw a little picture. Okay, here's my function. This is x of t. Yeah, I'm just doing it for a scalar. Okay, it's a scalar function, just so we can plot it. Now, if this is x of t and this is t here, what does it mean to increment or to perturb, you should say, the function? What do you have to do? Can you draw it for me? Suppose I drew another curve here. Right? So this is x of t, and this amount here is my increment. And this is my incremented value. I'm not going to assign it any notation yet. How am I going to represent this increment? Can I use this thing called delta? Because delta increments a point, right? What am I doing here? I'm incrementing every single value of t, right? At each instant of t, I'm doing an increment. I have to, right? I have to increment the whole function, right? I'm not just incrementing a point. I'm incrementing the entire function. So we don't use this notation delta. What we use is we use this notation called little delta, delta x of t. So the new result is x plus delta x, right? And if you want to be real clear here, it's x of t plus delta x of t. And the notation that we use is we say delta x of t. But over here, what do we normally call this delta? Is this thing over here is normally what's called a difference. It's the difference between the two values of x. So in other words, delta x, if I have another value y, which is equal to x plus delta x would equal y minus x, right? Over here, I don't use that notation. I use a little delta. What this is this is called the variation in the function x of t. How does x vary? We don't talk about differences. We talk about variations. Because variations are what drive changes in entire functions. We're varying the whole function, right? What does this mean in a more sort of layman sense? It's saying that give me some function. I don't care what it is. The result of varying it gives me back what? So what is this thing here? What kind of quantity is that? It's a new function, right? So this can't have the same meaning as what this has over here because this is a new point, right? It's not a new function. So here I have points, here I have functions. It gets back to the whole argument I'm trying to make here, which is that you have to get this basis straightened out before you get into optimal control at all. If you don't understand the difference between variations and differences, this isn't going to make any sense whatsoever, all right? We are not dealing with points when we're doing functional minimization. We're dealing with functions, all right? So that's the first thing I wanted to just go over. So the next thing we're going to talk about is we're going to talk about, sort of in more formal sense, how we actually write this stuff down. So that was my sort of overview. And then we're going to go on to the first basic problem in functional minimization. So the first thing is that we do it this way. We say, if I say Q is an element of Rn, then what I can do is, suppose I say f of Q plus delta Q, all right? What that is that's now the increment of a function. What's it going to be? Well, it's going to be the value, well, if I say f of Q minus f of Q plus delta Q minus f of Q. This is what's called the increment of the function f, where the input is a vector, all right? Now, the next thing I do is I say this. Suppose I have Q of t is a function. So what I'm saying is that Q of dot is an element of this set omega, all right? Now what I'm saying is that I can do this. I say J, which is my functional now, of Q plus delta Q which is a little delta now, minus j of q is the increment of the functional j. Notice that the difference here is that this is not a point, so I don't use a delta, a big delta anymore. I use a little delta. All right? And the key thing in all of this is that you have to understand that these are not the same thing. So really I should draw a line here. Okay? Because one applies to points and one applies to functions. So the next thing we talk about is we talk about this concept of minimization and maximization. Well, what does it mean to say that I've constructed a minimum or I found a minimum of a function? So if I found a minimum of a function, we say that Q star, which is an element of Rn, is a local minimum of f of q if the following is true. F of q star plus delta q is less than or equal to, or sorry, greater than or equal to, f of q star for all delta q in a neighborhood of q star. All right? That doesn't tell me anything about anything else other than nearby. If it turns out, if this statement, the above statement, is true for all delta q, then then q star is a global minimum of f. Okay? So we only have a global minimum if it doesn't matter how big I make that increment. I can make it as big as I want, and I still wind up such that this function value at q star is smaller than it is everywhere else. There should be a under. Now the next thing we talk about is we talk about a functional. So in the case of a functional, though, we have to be a little bit more careful because we don't talk about minima and maxima of functionals, because we do, but we don't use the same terminology. Instead of using the term minima and maxima, we use the term extrema. We say the extrema of a function. So what we do is we say this. We say that if, suppose that we say let x be an element of omega, and we say the function x star which is an element of omega, is a minimum of the functional j if what is true. So what would have to be true here in order for this to sort of do this paradigm? We would say that it's a local minimum if what is true. If j applied to any function x minus j applied to x star is what? If I take the difference between these two, what do I get? What should I get if this is a minimum? Should this be bigger than 0 or less than 0? Should be bigger than 0, right? Now notice that what goes in here is a whole function, not just a point. So I'm evaluating the whole function. And we're going to go through and we're going to start by doing a simple or sort of the basic problem in calculus and variations to do this. This now leads to the next thing I'm going to talk about, and then I'll do the basic problem, which is for points, we use what we call ordinary calculus. That's the calculus you've all learned. But for functions, or I should say for functions, let's not say for points, so for functions. And for functionals, we use what's called calculus of variations. So where does this term come from? Well, let's go back to what I talked about earlier. Remember, I talked about here the difference between 2 points, and here I talked about the variation of a function, right? So when we're trying to do calculus on functionals, we have to deal with variations. So we call it calculus of variations, not ordinary calculus. Ordinary calculus is about differences. We deal with differences between points. We're not doing ordinary calculus. We're doing calculus on functions of functions. So calculus on functionals, which means that we have to use what we call calculus of variations. So the way we do this is we deal with this thing through this concept of variation. So the most basic problem that we deal with in calculus of variations, this is like the classic problem that comes up in all of this, in this entire subject. And we're going to start with this, and then we're going to work our way forward, which is that suppose I have the following functional. I've got j, which is a function of x of t. It's also a function of x dot of t. And it's equal to this. The integral from t0 to tf of a function L of x of t, x dot of t, and t dt. Okay. The input is this function x. There's also the derivative of x. So I'm inputting both of these, all right, into this. And what I want to do is I want to determine a condition. So the goal of this is determine a condition that provides an extremum of j. What does it mean to have an extremum of j? It means that, remember, and I'm going to go back to what we did last lecture. You remember in ordinary calculus that if you have a function f of x and you want to determine a critical point, remember we called them critical points, take the first derivative and you set it equal to 0 if the minimum or maximum lies on the interior of the interval, right? So let's assume that that's the case for right now. What do we do when we're all done? We set that derivative equal to 0, and then we solve for those critical points, right? But in this case, I don't have a function. I have a functional. So what I'm trying to solve for is I'm trying to solve for a function. I want to know the function that tells me what the extremum is of the functional, meaning that I want to know, give me this function x of t, such that when I plug that in here, I wind up with a situation that if I found the minimum, if I plug in any other function, I wind up with a bigger value of the functional than I did when I actually plugged in the extremum value, right? So how do we do this? So we have to do a couple of things here. Well, the first thing we do is we have to somehow perturb that functional, right? So what we're looking for is, in the case of ordinary calculus, we'd set the first derivative equal to 0, right? And then we'd solve. In the case of this, what we do is we want to set the first variation in the functional equal to 0. What this means is it says first variation in the functional j is 0. You could say set the first variation in the functional j to 0. So what we want to do is say 2. So how are we going to do that? So how are we going to do this variation? So let's think about this for just a minute. If I take the variation in j, that's going to equal the variation in this thing, which is a function of x of t and x dot of t, right? Forget about the integral for just a minute. So how am I going to do that? Well, what I have to do is I somehow have to vary these, right? I have to vary x of t, and as a result, I have to vary x dot of t, right? So if I do that, I get this. I've got the variation in the integral from t0 to tf of L of x of t, x dot of t, and t dt. And I want to set that thing equal to 0. Now, in order to do this, I need to vary everything in here that changes. What changes in this? So in other words, I'm going to assume here, let's make this problem really easy. Assume the following, which is that x of t0 equals x0, and it's fixed, and x of tf is equal to xf, and it's also fixed, and t0 and tf themselves are fixed. This is the easiest problem in calculus of variations. What does this look like on a plot? I'm going to do another plot here. Change this plot, make it a little bigger. What it says is that here's t0, here's tf, here's x at t0, here's x at tf, it says that these values are known and they're fixed. T0 is fixed, I can't change it. X at T0 is fixed, I can't change it. Same thing is true at TF. There's a function that takes me from here to there. How many different functions will take me from here to there? A whole bunch of them, right? There are all kinds of functions that will take me from here to there. Right? Which one do I want? I want the one that makes this functional as small as possible. Right? That's what I'm looking for. So what I'm trying to determine is I'm trying to determine this thing that I'm going to call x star of t. It's the one that makes that functional as small as possible. So now look at this functional. Forget about the variation. Just look at the functional. What do I plug in here that can change the value of this? L is some known function. Okay? I know L. What I don't know, what do I not know? Is there anything I don't know? Could be something. No. I haven't found x star. What is the unknown in this? If I gave you the function f of t equals t squared, just a simple function, what's the unknown? T, right? Plug in a value of t, and then I get back a value for the function, right? What do I not know here that if I plugged it in, I would get a value for this functional? What's that? What else? More fundamentally than x dot.
L.
No, I know L. L is a known function. What are you having trouble with?
T.
Is this a function of t? How many people think this is a function of t? Yes or no? Is it a function of t? Yes, it is? You sure? You're having trouble with this, aren't you? Is it a function of t?
No.
Why not? T is a dummy variable of integration in here, right? When I'm all done, do I get something that's a function of t? What are you having trouble with? If I give you a concrete example, you won't have trouble with this. But what I'm trying to get you to do is stop thinking so concretely. Because if you think that concretely, then this just becomes a number plugging exercise, and I don't want you to do that. Let's suppose I gave you this functional. J is equal to the integral from 1 to 5 of t squared dt. Is that a functional? Or no, let's not do that. Let's say x squared of t dt. Is that a function, or is that a functional? Well, what is it? Why is it? It's a function of a function, right? What's the function? X of t, right? Right? X of t is the function, right? It's a function of a function, right? Now, if I say let x of t equal t squared, now what happens? What's the value? So when I say j applied to t squared, what do I get? Go ahead and do it. I get the integral from 1 to 5 of t squared dt, which is equal to t cubed over 3 evaluated from 1 to 5, which is equal to 5 cubed over 3 minus 1 over 3. Right? Is that a function of t? It's not. Is it a function of t? Yes or no? What if I change the function? What if I say let x of t equal cosine of t? Now what do I get? I get j applied to cosine of t is equal to the integral from 1 to 5 of cosine squared t dt. I don't want to integrate it. But is that a function of t? It is? Is it really? Is it any more a function of t than this is? Why is this a function of t? Because you can't just come up with a nice clean answer for it? I'm all done integrating this. What do I get? What do I get? You get a real number, right? Can a real number be a function of t? Absolutely not, right? This is not a function of t. Is that a function of t? I'm going to go back and ask you this. It's not. It cannot be a function of t. T is the variable of integration, right? Any variable of integration the result cannot be a function of the variable of integration. It's a dummy variable. I could replace this with anything. Sigma, Q, alpha, beta, gamma. It doesn't matter what I call it. I can call it whatever I want to call it. This is not a function of the variable of integration. It's not a function of t. So what doesn't vary in this? If it's not a function of it, what can't vary? The only things that can vary in here are these two quantities. Why can't t vary? Because t is the independent variable, right? It's going from t0 to tf. It can't vary. It is what it is. It's the variable of integration. It goes from this value to that value. It doesn't vary. The only things that vary are these two things. These are the quantities that can vary. If I change these quantities, I change the value of this functional, just like I did over there. I gave you a concrete example, right? I said the functional is x squared of t dt. If I plug in t squared, I get one value. If I plug in cosine of t, I get a different value, right? In both cases, I'm plugging in a value, I'm plugging in an entire function and getting back a number, right? I want to know in this case, what is that particular function, x of t, that makes this thing as small as possible? Clearly, if I keep plugging in different functions over there, I'm going to get different numbers, right? And there's going to be some function that's going to wind up giving me the smallest number possible. In this case, it should be pretty obvious. What is that function that minimizes this integral? It's not obvious, I guess. It should be fairly obvious. What's the function that minimizes this integral? 0, right? Because I'm squaring it, so it doesn't matter what I do. The only function that's going to minimize this is going to be 0. If I put any non-zero function into this, I'm going to get a non-zero value of the integral, right? This thing can never be less than 0. It's the integral of something squared, right? So it has to be a positive quantity. So the thing that minimizes this is a trivial problem. I just gave it to you just so that you could see what was going on. Now, let's go back over here, right? This is hard. Okay, so if all of a sudden you guys find, wow, this is really hard now, good. That's the way it should be, all right? It's going to make you work harder because this class is hard, all right? This stuff is hard. It's really hard, and it requires a lot of thought and a lot of time and a lot of patience. None of this stuff comes easily. It's not obvious, all right? So never use the word obvious in my class. There's no such thing as obvious. So if I say, is it obvious, immediately you should get everybody in the room should say no without even thinking about it. The answer should be no, all right? That's immediate, without any delay. You should say no, it's not obvious, right? There are some things that are obvious. Even then, you should still say no, right? Because you're not sure. So now, I want to minimize this, all right? So I want to take the variation of the integral from t0 to tf of L of x of t, x dot of t, and t dt. And I want to set that thing equal to 0 when I'm all done. Okay. Now, you just told me that the only things that can vary are x and x dot, right? So this variation cannot affect t0 and tf because they're fixed, clearly, right? So when there's no variation in t0 and tf. I told you that they were fixed, right? So they can't vary. So what can I do with this variation mathematically? It doesn't affect the endpoints of the integral. What can I do? I can move it inside to the integral, right? So this is equal to the integral from t0 to tf of the variation in L of x of t, x dot of t, and t dt. Now, let's look at this variation. If I take the variation in L, right, which is this is a function of x of t, x dot of t, and t, right? This is going to equal, well, if I do it to first order, I'm going to keep everything only to first order. I'm going to drop all the higher order terms, right? It's going to equal what? The partial of L with respect to x times the variation in x plus the partial of L with respect to x dot times the variation in x dot. Because these are the only things that can vary, right? But it does not include the last term. Notice there is no partial of L with respect to t. Why? Because I'm integrating t out of this integral, right? It's not a function of t. We already got through saying that. So there cannot be any variation with t because it's not even a function of t. So it makes no sense to say that there's a variation with respect to t because t is being integrated out. So now what I do is I plug this. So I'm going to say approximately, right? So I could say it that way or I could say this way, plus higher order terms. But what I'm going to do is I'm going to drop the higher order terms. So I'm only looking at the first derivative. Why do I do that? Well, in calculus, you do the same thing, right? If you want to find an extremum, you drop all the higher order terms and you look at the first derivative and see when the first derivative is equal to 0. Clearly, the increment of the function has higher order terms associated with it, right? But you're only holding everything to first order. So the same thing here. We're only holding everything to first order. So now what we do is we say, all right, I've got that part out of the way. So now my variation becomes this. So this whole thing becomes the integral from t0 to tf of the partial of L with respect to x times the variation in x plus the partial of L with respect to x dot times the variation in x dot. And I'm going to set that equal to 0. The whole thing is integrated over t. And I'm going to set that equal to 0. That's my first variation. That's the first variation in that functional. So if you don't remember that, that's the same thing as the first variation is equal to 0. Same thing. Okay. Now, what's true about the variation in x and the variation in x dot? I have a function, x of t. I have its derivative, x dot of t. I take the variation in x. Is the variation in x dot independent of the variation of x? Why not? Because x dot is not independent of x, right? X dot is the first derivative of the function x, so clearly it depends on x. Otherwise, you can't take the derivative, right? The derivative depends upon the function you're differentiating, right? So if I've got a function, x of t, its derivative clearly depends on x, so the variation in x and the variation in x dot have to be dependent upon one another. They can't be independent, right? So I need to get this in a form where I get it all in terms of a single variation where nothing else is in the problem except for that one variation. So I somehow have to unify these two terms. But I can't unify these two terms if I keep this in here. So what I do is, I do this, is we take the integral from t0 to tf, and we keep the first term the way it is. But now the second term, I'm going to do something with. What this looks like is, does this look like anything that you've ever seen before? Yes? No? Let's do it in 2 steps if you haven't seen it before. What about this? You ever seen this before? This is an aside. So here's my aside. Okay? What is the integral of let's do it the right way. X of t, y dot of t, dt. What can you do with that? Someone ever taught you how to do something with that before? What's that called? It's called integration by parts, right? This is u dv, right? So this is equal to u v minus the integral of what? V du. This is u and v. So y x dot dt, right? So I've got 5 minutes, right? 5 minutes. So I can do that here. That's my aside. It's integration by parts. So I can integrate that second term by parts. So what I get when I'm integrating by parts is the integral from t0 to tf of the partial of L with respect to x times the variation in x dot, variation in x dot dt is equal to what? If I call this u and I call this dv, I get uv, which gives me the partial of L with respect to x dot times the variation in x evaluated between t0 and tf minus the integral from t0 to tf of what? I get d dt of the partial of L with respect to x dot times the variation in x dt. uv minus integral b du. Right? So when I do that and I plug this in over there, I get the variation in j is going to equal this. The integral from t0 to tf, I've still got this first term, the partial of L with respect to x, minus now d dt of the partial of L with respect to x dot, the whole thing times the variation in x dt, and I've got this term over here, plus this term over here, the partial of L with respect to x dot times the variation in x, the whole thing evaluated between t0 and tf, and that has to equal 0. Yes? Okay, now, what this says is, it says that this plus this has to equal 0, but let's look at this a little bit. These variations here are only affecting the endpoints of the interval. What's the variation in x at t0? It's 0 because it's fixed. What's the variation in x at tf? It's also 0. So this whole thing is 0. I don't need to worry about it. So I'm left with this thing up here. Has to equal 0. It always has to equal 0, no matter what my variation is. What this says is it says this integral must equal 0 regardless of what this thing is over here. No matter how I vary x, this thing has to equal 0. What's the only way that this thing can equal 0 for all variations in x? This whole thing inside the square braces has to equal 0. So what this tells me is it tells me that this has to equal 0. The partial of L with respect to x minus d dt of the partial of L with respect to x dot has to equal 0. That's what's called a first-order necessary condition to determine the extremum. It's not an extremum. It's a first-order necessary condition. Remember I said determine a condition that would allow me to find the extremum. It doesn't tell me what the actual extremum is. It's a condition. And I don't think all of you have taken my dynamics course, but does anyone recognize this who's taken my dynamics course? Yes? What is this? This is Lagrange's equation, right? So this is the first variation of the integral, where the integral is a function of this thing L, which is itself a function of x and x dot. And it says that the necessary condition for optimality for that problem, when the endpoints are fixed, which is what I gave you here, a fixed endpoint problem, it says go from A to B, basically, is what it says, right? Is the Lagrange equation. This is actually the other way that people derive Lagrange's equation. Turns out that if you have a Lagrangian, if you take I mean, I don't think all of you have taken dynamics. I don't want to go too much into dynamics. But if you remember, for those of you who have taken dynamics, what's the Lagrangian a function of? It's a function of your generalized coordinates and your generalized coordinate rates, right? So it's a function of position and velocity. This functional is also a function of, you can think of this as position and that being velocity, right? So it's a function of the generalized coordinate and the generalized coordinate rates. The minimization of that functional, if L were the actual Lagrangian for a mechanical system, is the Lagrange equation. It's amazing how that works out, isn't it? They have nothing to do with each other, right? One's physics, one's math. They give you the same answer. Right? I always find that really strange because they have nothing to do with each other whatsoever. One's just a made-up math problem. The other one is an actual physical problem that comes from Newton's laws. I mean, you actually have something that's Newtonian in its nature. The thing is that this integral that I asked you to minimize, the original one here, this is what's called the action integral. This is Lagrange's action integral. And, of course, it comes from what's called the principle of least action. It says that physical systems always take the path of least action. You ever heard that phrase? Just take the path of least resistance? All physical systems take the path of least resistance. So even when you're really frustrated with something and you can't find your way through it, you are taking the path of least resistance by definition because it's physics.
So by definition, you are, even if you're pulling your hair out trying to solve a problem and you can't figure out what you're doing, you are taking the path of least resistance. So always remember that. So whatever you're doing, you're taking the path of least resistance. You may not believe it, but you actually are. So that's it for today. We'll go into more detail.